Let's examine a right triangle to understand the Pythagorean theorem. This fundamental relationship is one of the most important concepts in geometry. We'll label the sides of our triangle. The base is labeled A and measures 4 units, the height is labeled B and measures 3 units, and the hypotenuse, which is always the side opposite the right angle, is labeled C and measures 5 units. What makes this a right triangle is this special 90-degree angle, which we mark with a small square symbol. This particular angle is the key feature that allows the Pythagorean theorem to work. The Pythagorean theorem tells us that in any right triangle, c squared equals a squared plus b squared. The square of the hypotenuse equals the sum of the squares of the other two sides. This relationship only works because of the 90-degree angle. Let's verify this with our triangle. We have c equals 5, a equals 4, and b equals 3. So the theorem states that 5 squared should equal 4 squared plus 3 squared. When we calculate the values, 5 squared is 25, 4 squared is 16, and 3 squared is 9. So we have 25 equals 16 plus 9. Adding 16 and 9 gives us 25, which confirms that 25 equals 25. Our triangle perfectly satisfies the Pythagorean theorem, as all right triangles do. It's crucial to understand that the Pythagorean theorem only applies to right triangles. If a triangle doesn't have a 90-degree angle, this relationship between the sides won't hold true. The 90-degree angle creates a unique geometric relationship between the three sides. This precise angle ensures that the area of the square built on the hypotenuse equals the sum of areas of squares built on the other two sides. If we were to change this angle to anything other than 90 degrees, the Pythagorean relationship would break down, and we'd need different formulas to relate the sides. So remember, whenever you see a right triangle, you can apply the Pythagorean theorem to find unknown sides. The right angle is what makes this powerful relationship possible. Let's explore the Pythagorean theorem, which reveals the beautiful relationship between the sides of a right triangle, one of the most fundamental concepts in geometry. In any right triangle like this one, we have a special relationship. The side opposite to the right angle is called the hypotenuse, labeled C in red. The Pythagorean theorem tells us that the square of the hypotenuse equals the sum of the squares of the other two sides, A and B. Let's connect each part of this equation to our triangle. This helps us visualize what the formula actually means. The blue side, labeled A, appears in our equation as a squared. The green side, labeled B, appears in our equation as b squared. And the red side, our hypotenuse labeled C, appears as c squared on the left side of the equation. What makes the Pythagorean theorem so powerful is that it works for every right triangle in existence. The specific lengths may change, but the relationship c squared equals a squared plus b squared always holds true. Take a look at this small right triangle. Even though its sides are shorter, the relationship c squared equals a squared plus b squared still holds perfectly. If we measured the sides and did the calculations, the math would check out exactly. Now here's a medium-sized right triangle. Again, the sides have different lengths, but the same mathematical relationship applies. The square of the hypotenuse equals the sum of the squares of the other two sides. And with this larger right triangle, we see the same pattern once more. No matter how we stretch or shrink a right triangle, as long as it maintains that 90-degree angle, the Pythagorean relationship remains true. This consistency is what makes the Pythagorean theorem so powerful in mathematics. It gives us a reliable way to find unknown sides in right triangles, which is incredibly useful in fields like construction, navigation, and engineering. Remember that the Pythagorean theorem states that c squared equals a squared plus b squared. In everyday terms, this means that if you know the lengths of any two sides of a right triangle, you can always calculate the third side using this formula. Let's explore one of the most famous mathematical relationships, the Pythagorean theorem, using a visual approach that helps us understand why it works. We'll start with a right triangle. The right angle is shown at the bottom left corner, and this triangle has three sides that we'll investigate. Let's label our triangle. The vertical side is A, which in our example is 3 units. The horizontal side is B, which is 4 units, and the longest side, called the hypotenuse, is labeled C. The Pythagorean theorem is about areas of squares. So let's draw a square on each side of our triangle. We'll make the square on side A blue, the square on side B green, and the square on the hypotenuse C red. Each square's area equals the square of its side length. The blue square has area A squared, which is 3 squared or 9 square units. The green square has area B squared, which is 4 squared or 16 square units. And the red square has area C squared. To better see these areas, let's divide the squares into unit squares, each representing 1 square unit of area. These lines show how many 1 by 1 squares fit inside our larger squares. The Pythagorean theorem states that a squared plus b squared equals c squared. In our example, this means 9 plus 16 equals 25, which is indeed the square of the hypotenuse length. Now let's prove this visually by showing how the blue and green squares' areas combine to exactly equal the red square's area. First, we'll replace our large squares with individual unit squares. We now have 9 blue unit squares representing a squared and 16 green unit squares representing b squared, for a total of 25 unit squares. If we can fit all of these squares into the red square, we'll have proven the Pythagorean theorem visually. Watch as we move all 25 unit squares from the blue and green squares into the red square on the hypotenuse. Each unit square represents 1 square unit of area being transferred. Amazing! The 9 blue squares and 16 green squares fit perfectly into the 25 square units of the red square. This visually confirms that a squared plus b squared equals c squared. This colored equation highlights the relationship. The blue a squared plus the green b squared equals the red c squared. This relationship works for every right triangle, not just our 3, 4, 5 example. The Pythagorean theorem is one of the most useful relationships in geometry. It tells us that in any right triangle, the sum of the squares of the 2 shorter sides equals the square of the hypotenuse. Let's explore the Pythagorean theorem using a concrete example. We'll create a right triangle and verify the famous equation. In a right triangle, we have 3 sides. The 2 sides that form the right angle are called the legs, which we'll label as A and B. The longest side, opposite the right angle, is called the hypotenuse, which we'll label as C. For our example, we'll use a special right triangle with whole number sides. Side A has length 3 units, side B has length 4 units, and the hypotenuse C has length 5 units. Notice the small square in the corner. That's our symbol for a right angle, which is exactly 90 degrees. The Pythagorean theorem states that in any right triangle, the square of the length of the hypotenuse equals the sum of the squares of the other 2 sides. In mathematical notation, we write this as a squared plus b squared equals c squared. Let's verify this with our example. First, let's calculate a squared. When we square 3, we multiply it by itself. 3 times 3 equals 9. So a squared equals 9. Next, we calculate b squared. When we square 4, we get 4 times 4, which equals 16. So b squared equals 16. According to the Pythagorean theorem, we need to add these squared values together. So we have a squared plus b squared, which is 9 plus 16, giving us 25. Now let's check the other side of the equation. C squared is 5 squared, which is 5 times 5, equal to 25. Look at our results. A squared plus b squared equals 25, and c squared also equals 25. The 2 sides of our equation are equal, which confirms the Pythagorean theorem for this triangle. This 3, 4, 5 triangle is a famous example of what we call a Pythagorean triple, a set of 3 whole numbers that satisfy the Pythagorean theorem. Other examples include the 5, 12, 13 triangle and the 8, 15, 17 triangle. These special triangles are particularly useful in construction and engineering. The Pythagorean theorem is incredibly important in mathematics and the real world. It helps us find unknown distances, calculate areas, and solve problems in navigation, construction, and even in computer graphics and game design. Here we have a right triangle. The small square in the corner indicates the 90-degree angle. We know that side A is 5 units and side B is 12 units. We need to find the length of side C, which is the hypotenuse, the side opposite to the right angle. For any right triangle, the Pythagorean theorem gives us a relationship between all three sides. It states that c squared equals a squared plus b squared, where c is the hypotenuse. To solve our problem, we'll substitute what we know. Side A is 5 and side B is 12, so we have c squared equals 5 squared plus 12 squared. First, let's calculate each squared term. 5 squared equals 5 times 5, which is 25, and 12 squared equals 12 times 12, which is 144. Now we add these values together. 25 plus 144 equals 169. So we've determined that c squared equals 169. To find the value of c itself, we need to take the square root of both sides. The square root of 169 is 13, so c equals 13 units. Looking back at our triangle, we can now confidently state that the hypotenuse has a length of 13 units. This triangle with sides 5, 12, and 13 is actually a special case known as a Pythagorean triple, where all three sides are whole numbers. The Pythagorean theorem is a powerful tool that works for any right triangle, allowing you to find any unknown side when you know the other two sides. Let's explore the Pythagorean theorem, one of the most fundamental principles in mathematics that relates the three sides of a right triangle. This equation states that in any right triangle, the square of the length of the hypotenuse, which we call c, is equal to the sum of the squares of the lengths of the other two sides, A and B. Let's visualize this with a classic example, a 3, 4, 5 right triangle. This special triangle has sides of length 3 and 4 units, with a hypotenuse of exactly 5 units. To visually prove the Pythagorean theorem, we'll draw squares on each side of the triangle. The area of each square represents the square of the corresponding side length. The green square has an area of 3 squared or 9 square units. The yellow square has an area of 4 squared or 16 square units. And the red square on the hypotenuse has an area of 5 squared or 25 square units. Let's verify this mathematically. 3 squared plus 4 squared equals 9 plus 16, which gives us 25. And that's exactly equal to 5 squared, confirming the Pythagorean relationship. The beautiful thing about the Pythagorean theorem is that it works for any right triangle. Let's transform our triangle and see the relationship hold. As we transform the triangle to have sides of length A nu and B nu, watch how all three squares automatically adjust their areas. The relationship between these areas remains constant regardless of the triangle's size. Let's check the math. A nu squared equals A nu, and B nu squared equals B nu, B nu. Adding these gives us A nu plus B nu, which equals C nu squared, or C nu, C nu. The theorem holds perfectly. This pattern continues for all right triangles. Whether they're small or large, the square of the hypotenuse always equals the sum of the squares of the other two sides. The Pythagorean theorem isn't just a mathematical curiosity. It has shaped how we understand and interact with the physical world for thousands of years. In architecture, the theorem helps ensure buildings are square and stable. Navigators use it to calculate distances and plot courses. Engineers apply it in countless ways, from designing bridges to creating precision tools and technology. Discovered over 2,000 years ago, this elegant relationship has been proven in many different ways and continues to be essential in modern science, engineering, and mathematics. C squared equals A squared plus B squared, a simple equation that connects geometry, algebra, and our physical world in a profound and beautiful way.